Welcome to another video. This is a problem that was sent to me more than once and I ignored it because it gave me the vibes of tetration because I can see a tower of x's in the denominator of an integral. So I said, no, I'm not going to do that because I knew somehow the solution was not going to be something for the general calculus student. But I gave it a shot today and I got surprised. Let's get into the video. So the first thing I did, like I would suggest to anyone, whenever you get the exponent being a function, the base also being a function, is to just do a u substitution when you're integrating, because then you're going to end up with a product and you might be lucky something works out. So what I did was I said, let u be equal to, you know what, I'm going to write it as 1 over x to the x, which is the same thing as x to the negative x. Okay, so then I can say du, if I differentiate oh no, remember you need to bring it down, so we need to introduce the natural log function. So I'm going to say ln of u will be equal to negative x ln of x. And now I can differentiate both sides. So if I differentiate ln of u, I'm going to get 1 over u du. And if I differentiate this side, it's going to require the product rule. So let me put the negative sign outside. And then if I differentiate this, it's going to be differentiate the first, keep the second, which is going to be ln x, plus keep the first, differentiate the second. That's going to be x times 1 over x when I differentiate this, which is just 1. So remember, and I have dx. So the point of u substitution is to change the variable from x to u and to also change the variable of integration. And this dx has to change to du. So I need to isolate du, but everything else has to be in terms of u. And this is where I got stuck because it was impossible for me to convert this to something in terms of u. If I want to write ln x in terms of u alone, it's going to be ln x will be minus ln u divided by minus x. So what exactly is x? You see, it was impossible for me to do it. This is where I gave up and I went back. Let's start afresh. We really don't have to start afresh. Let's keep going. Instead of taking the derivative so I can change this to du, what about if we do some transformations? Look, if I raise this to power e, I can also raise this to power e, like this. And guess what? E to the ln of u is just u, and this can be written as e to the negative x ln of x. That's it. So that the original integral, this integral here, I can be written as the integral from 0 to 1 of e to the negative x ln x dx. Now, I have not changed anything. I just rewrote this integrand to look like this. Now, can this be easily integrated? The answer is no. But we can do something with the infinite series that represent e, because from there we might be able to get something nicer. Let's recall. Recall that e to the t can be written as the sum from n equals 0 to infinity of t to the n over n factorial. This is how we write e to anything. It is that thing to n divided by n factorial, and you just take the sum of it. You keep adding. It's an approximation because this is a transcendental number and it's irrational. So we know what's sitting on top of e is t. So we just need to say this is our t now. So we can say I is equal to the integral from 0 to 1 of what we have here, which is going to be, so instead of us writing this, I'm going to write this sum. It's going to be the sum from n equals 0 to infinity of this minus x ln of x raised to power n divided by n factorial dx. Okay, now you're gonna say, what in the world is this? How is this supposed to make it easy? But my mind is working because I know whenever I'm doing an integral and I see n factorial, actually this was where my eyes opened, the gamma function is going to show up. Okay, but I just need to be able to rewrite this expression so that it looks like the gamma function, and then the answer is just going to pop out. Okay, so let's keep going. I can say that this is the same thing as the integral from 0 to 1 of this sum from n equals 0 to infinity of, this is, you see this negative x ln x raised to power n can be written as minus 1 raised to power n times x raised to power n times ln of x raised to power n. Each of them will be raised to power n. It's good now. Now, what can I do with this? The thing is, because this is a sum, everything that contains n must be inside the summation sign. Okay? So I cannot pull out anything that contains n outside of the summation sign. But a question I want to ask is, can I switch these? Everything will still be inside the summation sign, but now the integral sign is going to be on the inside. Can I switch them? The answer to this one is yes. Now, there are three theorems that are actually relevant here, but the biggest one is what you call the dominated convergence theorem. Okay, it is more like you using the alternating series, because here, this is an alternating series. Now, the value of x is less than 1, is between 0 and 1. So when you have almost everything between 0 and 1, you can see everything is it's gonna converge ultimately, and every individual term is integrable, is convergent, is finite. I don't want to dwell on that, but if you are solving a problem like this, you'll already see that the dominated convergence theorem is what they want you to use to switch these two, and that's what I'm going to do. So I'm going to say that this I can then be written as the sum dx. Okay, now with this, things are a bit nicer because this is a constant, it's a number. You can always move a constant to the back of the integral sign. So I am going to do that. This is now equal to the sum from n equals 0 to infinity of, I pull this to the back, it's negative 1 to the n over n factorial, and then I have the integral from 0 to 1 of, now I'm getting excited because the answer is about to show up, dx. Okay, at this point we need to do a bunch of basic calculus and algebra, because it is from here we're going to obtain the gamma function that I talked about. Okay. Now let's recall again the nature. Just as we needed to know this, you also need to know that n factorial is written this way. That's the gamma of n plus 1, which is clearly something that looks like this. I would write it as the integral from 0 to infinity of, let's use t. Let's say it is t to the n e to the negative t dt. So if I can transform this one to look like this, I've gotten n factorial. And the mission is so that that n factorial that comes from here can get rid of this guy. And then we don't have to deal with the factorial anymore. But while we're trying to do that, something else is going to show up and we'll take care of it. So look, this is what we need. We need something like this. So what I'm going to do is, I'm going to look at the problem here. The problem here is the ln of x. Okay, so I'm going to replace ln of x with something, let's say t, and then we'll see what the algebra and the calculus will get for us. Let's get rid of this. So let's say that t, let me write it here, t equals ln x. Okay, so I'm going to continue this. Let me just prepare. So you see the substitution, n equals 0 to infinity. We have an integral. The bounds are going to change ultimately. It's going to change here. Look, let's even start with the bounds. If t is ln x, remember I need it to look like this. The integral from 0 to infinity of t to the n e to the negative t dt. So I need this. So if t is ln x, then when x is 0, ln 0 is going to be negative infinity. So I'm going to have negative infinity here. Still doesn't look like this. Okay, but let's keep going. But if you don't want it to be negative infinity, you can say let negative t be ln x. That's a faster way. Okay, let negative t be ln x, so that means t is negative ln x, right? Okay, this implies t is negative ln x, so that when x is 0, this is negative infinity times negative, that gives us positive infinity. So I'm going to do this. Nice. And then when x is 1, this is going to be ln of 1 is 0. 0 times minus 1 is still 0. So I got 0 on top. Perfect. I don't have to do it twice. Okay. Now what's the next thing? I need this to be, what do I have? Now x raised to power n, I need to know what x is. From this relationship, I know that e to the negative t will be e to the ln x, which is x. So I can replace x with e to the negative t here. So x to the n will be e to the negative t raised to power n, which is negative tn. Okay? And we already said let ln of x be t. So this is t to the n. No, let ln of x be negative t. The problem is still there. So when I replace ln of x, I have to replace it with negative t. So it's going to be times negative t raised to power n. Okay, I can break this down actually into negative 1 raised to power n times t raised to power n. Yeah, I'll do that. So the only thing left is to replace dx. Let's go here. If e to the, let's use this one. If we differentiate this, we're going to have dt. If we differentiate this, we're going to get negative 1 over x dx. So that means our dx will be x dt negative 1. There's a negative 1. So we're going to end up, but what did we say x is? X is e to the negative t. That replaces dx. So that is times negative e to the negative t dt. So many things to write here. Okay, it looks like everything is looking juicy at this point. Oh, I'm missing something. I forgot to write the factorial. Not good. Okay, it's here now. So this long thing is going to become very short because this is what happens. This negative 1 to the n can also come back here and multiply this so that negative 1 to the n times negative 1 to the n is just 1 to the n, which is 1. N equals 0 to infinity. So we have 1 over n factorial. Nice. This e to the, this minus sign actually can help us flip this. That's 2. The third thing is I can write t to the n here. And this is e. So remember, when you multiply two things together, you add the exponent. So if I add these two, it's going to become e to the negative It looks like it's going to be n plus 1 t dt. It still does not look like this. See, everything is almost except this guy is not. I have negative n plus 1. I have to do a u substitution. I have to find another letter because I need it to be perfect. This guy can run around, but this guy cannot run around. So because I need this guy to just be negative t or another letter, I have to do another substitution. I'm going to use r. So I'm going to say, let r be n plus 1t. So that means that t equals r over n plus 1. And if I differentiate, I have dr will be equal to n plus 1 dt, which implies that dt will be equal to dr over n plus 1. And I think that's it. Oh, I need to check the boundaries. So when t is 0, what would r be? When t is 0, r will be 0. And when t is infinity, infinity times finite is infinity. So the bounds do not change. It's the same boundaries I'm going to be using, okay? So I'm not going to show that work here. So we have I equals the sum from n equals 0 to infinity of, we have 1 over n factorial. And then we have the integral, same bounds from 0 to infinity of, now we said t equals, what's t? R over n plus 1. R over n plus 1 will be raised to power n times e to the negative n plus 1t will be r. And we have our dt is dr over n plus 1. Nice. What do you see? This is the same thing as the sum from n equals 0 to infinity of 1 over n factorial times, look, I'm going to take out everything that has just n, okay, that you don't differentiate. So here, this is n plus 1 raised to power n in the denominator. This is n plus 1. Oh, so this is going to be like this. 1 over n plus 1 raised to power n times 1 over n plus 1. If you multiply these two together, you'll end up with 1 over n plus 1 raised to power n plus 1. That's what you get. And then the integral that comes after it will go from 0 to infinity, and you have r raised to power n times e to the negative r dr. This is n factorial from what I wrote initially. So we have found our factorial function, the gamma function of n factorial. So this is going to be from n equals 0 to, this is 1 over n. So it's now 1 over n factorial times 1 over n plus 1 raised to n plus 1 times n factorial. And this is equal to the sum from n equals 0 to infinity. This is going to cancel this, and our answer is n plus 1 raised to power negative n plus 1. Or you can write it this way. It is the sum from k equals 1 to infinity of k to the negative k. This is the answer I would write. Because again, if you say let k be n plus 1, you can easily adjust it, and you see that when n equals 0, k is going to be 1. Show that quickly. Let k be n plus 1. When n equals 0, k will be equal to 1. So instead of you saying n starts from 0, you can say k starts from 1. And you can replace this with k, replace this with k. Never stop learning. Those who stop learning, stop living. Bye-bye.